I welcome you all in today's webinar on earthquake monitoring and management, jointly organized by National Institute of Disaster Management, Ministry of Home Affairs, and National Center for Seismology, Ministry of Earth Science. There will be two sessions in today's webinar, inaugural and technical one. Major General Manoj Kumar Bindal, VSM, Executive Director, NIDM, and Dr. B.K. Bansal, Director, National Center for Seismology, will be joining us in inaugural session. For the technical session, we will be having three distinguished experts, namely Dr. G. Suresh, Scientist Staff, National Center for Seismology, Professor Ravi Sinha, and Professor Suresh Surya Prakash, Head GMR Division, NIDM. This webinar is also streaming live through NIDM's YouTube channel. So if anyone is facing any technical issue to join us in WebEx platform, they can connect us through YouTube. India's hazard profile shows that about 59% area of India is vulnerable to moderate to major earthquakes. In last few decades, country has witnessed many devastating earthquakes like Manipur 2016, Sikkim 2011, Kashmir 2005, Bhuj 2001, Chamoli 1999, and Latur 1993. There are many more, which cause significant loss of human life as well as physical infrastructure. The scrutiny of past earthquakes demonstrated that all type of buildings sustain damage if not designed properly. Collapsed structures are primary cause of casualties during any catastrophic earthquake. More than 90% of the casualties in past earthquakes in India have occurred due to collapse of houses and structures. The loss of life and property can be minimized significantly by ensuring better code compliance of upcoming constructions and undertaking seismic reporting of exiting buildings, thereby making them earthquake resilient. Strengthening the resilience of infrastructure and structure is emphasized in major frameworks guidelines for DRR. The very first agenda of PM's 10-point agenda on DRR also highlighted the need to mainstream DRR in development activities. Also, the Target 4 of Sendai framework exhorted to substantially reduce disaster damage to critical infrastructure and basic services. I hope today's webinar will be fruitful in brainstorming the challenges as well as robust solution to negotiate the adverse impacts of earthquake. Now, I would request Major General Manoj Kumar Bindal, Executive Director, National Institute of Disaster Management, for his keynote address. Over to you, sir.
Today is a very important webinar, and we have particular collaboration with the National Center for Seismology, who are responsible for the earthquake monitoring and the management. And a lot depends upon what they tell us in advance of any such disaster. And I thank Dr. B.K. Bansal, who is Director for National Center for Seismology, for collaborating with NIDM to hold such an important webinar, because earlier we had been speaking on structural and non-structural measures and how we can take care of an earthquake. But here today we are talking about at a much higher scale what we can do to ensure that before earthquake comes, everyone is aware of such things, and future development also takes into account the various results of such earthquake monitoring. And we have esteemed speakers in this particular session, Professor Ravi Sinha, who is known for his earthquake engineering, Dr. Surya Prakash, who is from NIDM, and Dr. G. Suresh from the National Center for Seismology, who are there. So first of all, I welcome them for taking part in this webinar, and I welcome all the participants who have joined with the hope that they will be able to learn something and also contribute. Their contribution is through the chat box, through the question answers, and learning is by listening very keenly to the speakers. Coming down to the subject of earthquake monitoring and management, we are all aware that earthquake is one of the most devastating natural disasters on Earth. Its effects can cover hundreds or thousands of square kilometers and cause damage to structure or infrastructures, facilities, results in loss of life and injury to hundreds of thousands of people disrupt the social and economic functioning of the affected area. Although it is impossible to prevent earthquake from occurring, it is possible to mitigate the effects and to reduce the loss of life, injuries, and the damages. Besides tsunami, earthquakes can create many more disasters such as liquefaction, landslides, earth ruptures, most prominently ground vibration. And this ground vibration can cause structural collapse, loss of lives, and property damage. So, research in the field of earthquake engineering is still required even in the country with low to moderate suspect level activity. We have studied, there is also a study conducted in China, which is called the Tremor Project, TREMOR. It talks about monitoring, it is a study on monitoring of the earthquake, and it is brought out very good lessons. As per the study, remote sensing satellites are presently used for many earthquake related activities. However, the revisit time, the temporal resolution is right now quite low. There is presently a very big gap of maybe up to several weeks, uh, which is a concern for earthquake response because timely data is critical. So the prospect of being able to earthquake forecast with a suitably long lead time, that is days or even weeks, is something which should be investigated further. And this is an area where we are lacking in a big way. A 17-second pre-warning to the Mexico earthquake this year was considered a very accurate and very advanced warning in the field of earthquake advance intimation. Navigation satellites are used for ground motion studies. So where one area where this technology can be further utilized, that is the space technology, is in vehicle tracking to during response effort to coordinate the visibility. So there are many ways we can use technology to help out in earthquake. But the whole thing finally comes down to uh, uh, how how well are we positioned to predict an earthquake? And that is the moot question for today. What are we doing that we are doing? There's so many space applications and technologies which are being used for management, like since this learned uh, participants, I will not speak in detail, but like global navigation satellite system, synthetic aperture radars, electro-optical sensors, magnetic sensors, thermal infrared sensors, and the GIS is being used very widely. And of course, telecommunication binds them all together. Japan, if you take the example of Japan, which is one of the most seismically active regions in the world, and it accounts for nearly 20% of the world earthquakes of magnitude 6 or greater. And they are also known for producing some of the most severe events, which examples have been talked about a number of times. So the government there restructured the basic disaster management plan to include development of new special countermeasures for earthquakes, enhancement of building codes, including retrofit of existing structures, and the establishment of a disaster reduction and volunteer day. So taking into account the lessons learned from Kobe earthquake of 1995, many seismological organizations were established and the scientific field of seismological measurements was significantly strengthened. NIED, that they call, was established to coordinate all these activities. On account of a geophysical setting, is highly prone to earthquakes of various intensities, varying intensities, I'd say. And the country has faced several devastating earthquakes in the past, resulting in a large number of deaths and severe property damage. Recently, for last 6 months, we are seeing large number of rise in number of small earthquake events all over the country and also in the Himalayan region. So as per the current seismic map, hazard map country, about 60% of India's land area is under threat of moderate to severe seismic hazard. And that is prone to shaking of intensity 7 and above. So this frequent occurrence clearly demonstrate that there is a need to have a system where we can give advance warning to the people. And the key observations in these areas was lack of awareness in people about the earthquake in advance, and of course the do's and don'ts and its consequences, and absence of mechanism to ensure earthquake resistant buildings. So that is again comes down to structural and non-structural measures, or engineered or non-engineering measures. But here today we are concentrating upon the ability to predict. It is necessary that we must adhere to all the bylaws, building codes to make a building secure. But National Center for Seismology has been working on this for years, and day by day they are increasing that capability. Like we had now Ministry of Earth Science, they had an earthquake monitoring and prediction and mitigation project, which is real-time seismic monitoring network, which consists of about 17 broadband stations. So it is within 15 minutes messages are sent. A 20 station VSAT based network has been established. Similarly, a precursor study was conducted by the Ministry of Earth Science, in which cities were launched. So this national program on earthquake precursors, NPEP, to was a launch to adopt an integrated approach for generation, assimilation, analysis of various earthquake precursory phenomena in critical seismotectonic environments in the country in a comprehensive manner. We require such a type of systems where all the scientific community, the researchers, they come together and contribute to help predict an earthquake much in advance, so that not even a single uh, casualty is there, not a single life is lost. That should be the first priority. The second priority is to ensure structural damages are minimized, so that the economic loss is also minimized. So with these two concerns, this today's webinar has been planned, that we will be hearing from experts as to what is being done for ensuring that earthquake monitoring and management is advancing in the correct phase, and what should be done in future, and how we all can come together to ensure a better earthquake resistant, or I'll say better prepare the community from damages of an earthquake, devastating damages of an earthquake. So with this, I will put a stop, because this is a subject we could talk for hours, but the experts are there, and I will like to listen to them, because they are experts in their field who have been working in this field for years, and their experience really counts, and this webinar is made is also to ensure that that experience is shared with the participants. So I finish my talk here. I once again thank National Center for Seismology for collaborating with NIDM, Dr. V.K. Bansal in particular, and his team, and from our side, Dr. Prakash and Anil Katar. Over to you, Anil.
Thank you, sir, for providing your valuable inputs on the webinar. Indeed, we need to enhance our technological capacity besides the strict implementation of building bylaws to reduce and mitigate the impacts of earthquake on our communities as well as built environment. To further address the participant, I would invite Dr. B.K. Bansal, Director, National Center for Seismology. He is also serving as advisor to Ministry of Earth Science. Over to you, sir.
Major General Manoj Kumar Bindal, my friend Dr. Surya Prakash, to whom I know for last so many years actually, Professor Ravi Sinha, my colleague Suresh, then other experts and the participants who are joining this webinar through webcast. I once again say hello to them, and I'm thankful to NIDM, Dr. Surya Prakash in particular, to give a thought to this kind of webinar, in fact, where the topic was chosen, such an important topic, monitoring and management. This is really the requirement of the day, I will say. And Major General Bindal has really put things in the right perspective, so I need not to do much about that. But coming back to where he left, I must start thinking about this earthquake prediction. Basically, if you see, the prediction effort are still on, though there is some kind of success in the past. It was in 1975, in fact, when this first very successful earthquake prediction took place in China. That was the Haichang earthquake actually, and it was very successfully predicted, and there was a lot of hope in the scientific community world over. But what happened very next year, there was a disastrous earthquake of magnitude 7 plus in Tangshan, where I think more than 2 lakh of people they killed and a lot of damage to the property. And we again started from zero. So what is happening actually, a lot of effort is there, like Japan, China, US also. In fact, in India, we also started about 30 years back. And we are really, working hard, in fact, still, like in terms of precursory studies, because it is started from Amritsar University, Guru Nanak Dev University, Amritsar, where this, precursory changes in helium and radon was started to take lead into it. And then slowly, we had set up a few multi-parametric geophysical observatories in the country as a very systematic national program, as you rightly mentioned, Major General Windal. So what has happened during the past, say, 15 years or so, a very good data set have been accrued by these observatories, and this is being really analyzed now. And some papers I'm sure you must have seen by Wadia Institute of Himalayan Geology, where they have tried to correlate with different geophysical parameter with the earthquake occurrence. But unfortunately, still what is happening that the correlation is not really very conclusive. We are working still in hindsight. When earthquake happens, we look in the signals, in the records, and then we try to correlate that, oh, this is the earthquake and this is the signal. But the issue is that until unless we really look into the real-time analysis of the data and we are trying to tell that, look, this is the anomaly in a particular parameter and there could be earthquake after 5 days or 3 days, and where it is going to happen, because earthquake prediction, as you know, unless it is really quantified in terms of its space, time, and size, it has no meaning. Particularly, it is not going to serve any purpose to the society, because you must have seen, at least we are receiving so many references in the ministry that some people are working or not working, rather they predict the earthquake, like one is in Banaras, Shakil, Ahmad, and all. So many people are really there. But anyway, barring those things, they are keep on happening. We must keep on doing our good work. One thing is very important, really, the earthquake early warning system, which you have also mentioned in your keynote address. This really should be taken up, and some work was started, in fact, about 7-8 years back at IIT Roorkee. You must have heard about them somewhere at least. So these people, they put about 100 stations in Northwest Himalaya in a small window of 70 by 40 kilometer. And what happened actually, this was a tested system in Taiwan. And we thought that it is really going to be really very useful in our country as a pilot study. But what happened in this Rudraprayag earthquake, which occurred in 2015, I think it was 5+ event, but it did not trigger. There was nothing actually. So particularly we lost little hope, and to our knowledge, it remained as a prototype because it did not serve the purpose. But somehow what is happening that people are not really aware. People think that if I put 100 system in an area, then they will be safe. So that is not the really case. Anyways, that system is still working, and we are very hopeful that in near future we should be able to improve upon that. And Uttarakhand government, which is supporting that project, they must be doing good work. But at the same time, we are also thinking parallelly, to have some kind of collaboration with the USGS, where they have recently launched in October 2019 a very good earthquake early warning system. So in case we are able to succeed, we will definitely going to put it again in a pilot phase, and hopefully it should be really helpful to in our effort of mitigation. So that is another point. Coming back to this hazard, particularly hazard donation is really very important aspect, and some work has already been done. But the again important issue that once the hazard donation is done on large scale, so-called micro donation, there must be some taker for that. Actually, the report goes, sometime in Almira and sometime it is goes to the stakeholder as well. But the utility of this report has to put in place really, which is not being used to its right requirement. But recently I had a meeting with NDMA, and there I impressed upon this point, and they were really appreciative, particularly member secretary, and he asked the state governments that at least they should start utilizing this report, and there is some action initiated on that. I'm really very happy that they have starting some action on that. So, and this effort really also need to be continued. As far as coming to monitoring, monitoring is of course the backbone of the every system, because though we are not able to give any kind of forecast at this moment, but until unless we really accrue the good quality data and analyze into details, we will not be able to really work on this aspect. So this monitoring, as you said, we have expanded the network in recent past. At present, about 115 stations, which are state-of-the-art system actually. They are working in real-time mode, and somehow the information which was we were used to give in the region of IMD more than an hour or so, we are able to give the information within 5 to 8 minutes. If you see the auto location software, sometime, not sometime, most of the time it comes within 3 to 4 minutes. But it need to be reviewed because sometimes there are false events. Because this station, they get triggered and event is located, because this is done in auto location mode. So it takes some time. So 10-15 minutes, you may really consider not a bad time. And we are really definitely going to improve upon that, because we have further plans to strengthen this monitoring network to by adding 300 more in say next 2-3 years. My colleague Dr. Suresh will be giving, I think, a detailed presentation what we have and what we are going to do. So we can leave that at this point of time. But 2-3 points which I would really like to emphasize are like this hazard thing. What we have these codes, building codes, they are there and they are really very good codes. But what I feel that they need to really convert it into simple kind of adaptability, simple kind of language, so that people who are not really very well educated or very well trained, they can also try to utilize those codes. Particularly if you go into hilly areas or remote places where the training of the people is not really very good. So we should really think about some kind of training on mason level, as well as how we can make use of this local material over there. It is really going to help us in a big way, since NIDM is playing a very good role in training, giving training to the different level. NIDM may consider this aspect also for their future program. And as far as National Center for Seismology is concerned, we are really more than ready to be with you anytime, whenever you feel that we both of us can really do little better. We would be very happy to join hands with you. And my colleagues are there. In fact, we have got 2-3 good people. We are trying to utilize this artificial intelligence also in locating earthquakes. I think Anil is there to tell me that time is over. So I am not really going to pull it very much. So with these remarks, in fact, I would like to close this remarks at this moment, and I would be happy to share my experience to the participants through whatever chat or email or phone call, etc. It will be pleasure for National Center for Seismology really to give some kind of response to these people. So thank you very much once again to Major General Hindal and Surya Prakash and his team, who were really more than ready and helped in many ways actually. Thank you very much.
Thank you, sir, for sharing your experiences apropos of prediction and monitoring of earthquake disaster and future approaches towards creating earthquake resilient environment. I thank both dignitaries for sparing their valuable time and enlightening us with their expertise. Now we move ahead for our technical session, but before that, before I introduce our first speaker of the day, there are some instructions for the participants. Question and answer session will be after the presentation of all the speakers. Participants who have any query can share through Q&A box that is on your right hand side, and it is requested to please avoid spamming Q&A box with greetings. So the first speaker of the day is Dr. G. Suresh. He is scientist staff and head of seismology division of National Center for Seismology, the nodal agency of Government of India for monitoring of earthquake activities in the country. He will be supervising us on the development of seismicity monitoring in the country. Over to you, sir.
Okay, thank you very much, Anil, and also I congratulate NIDM for arranging this series of lectures on various topics, and also I agree with the remarks of our director and also Major General Manoj Bindal, and he rightly said that for disaster resilient society. This seismological network is the backbone. This was told by this executive director as well as our director NCS. So I will go to my presentation. So this is for example, we know that earthquakes happens due to large release of energy, electric strain energy. Suddenly that has accumulated in the hypocentral region over decades of centuries or longer. So this is the earthquakes. This is a very short-lived phenomena. Everybody knows about that thing. And in the total, this seismic energy will travel through the interior parts of the earth. This is the only signal which completely travels the interior parts of the earth and brings the information about the interior parts of the earth. So and and so this is the from the so the for the to know the information about the source and the interior structure of the earth. So the monitoring of earthquake is very important thing. So in the total energy budget, so when the earthquake happens, a lot of energy will be released. In the total energy budget, only 12% of the energy budget, sorry, 7% of the energy budget, only very small fraction will be converted into the seismic waves. The remaining will go as the for overcoming the friction. This is the fault friction and the pulverizing the rock to expand the rupture area, and some part of the energy will go as heat. So this seismic waves which travels complete the interior parts of the earth and brings the information, and will tell about the source, and also will tell about the complete physical properties of the interior of the earth, and also it will explains the what are the faults in the region which are become active, and also it will tell about the nature of ground shaking, whether
Dr. Suresh, sorry to
Yeah.
disturb you.
Yes,
Can you
yes.
make your slides full screen because it is coming out very slow? Thank you so much.
Yes, yes.
Yes, thank you.
So the seismic waves will bring the complete information about the source, how the earthquake was occurred, what is the faulting mechanism, and also it will tell about the complete the physical properties of the interior of the earth, and also it will tell about the what are the active faults in the region, and also it will tell about the how the a particular area is experiencing the shaking, how how the ground shaking would be. So from measuring the small earthquakes, we can predict the strong ground motion from the future earthquakes. And also all this information will be useful for the seismic hazard analysis of the area. So so apart from that, the basic parameters, what is the size of the earthquake, what is the fault geometry, and all those information we will get from the monitoring of the earthquakes. This thing for recording the seismic waves. So I will tell about the arrival of the seismic waves from the different locations. We give the location of the earthquake. So location of the earthquake means where these parameters where the earthquake has happened. how far it is, what is the focal depth, how far is it deep, and then the travel time will tell about the information about the how much speed the wave has traveled, any low velocity regions are there, or what are the densities and physical properties of the medium it will tell about. And also the amplitude of the recorded ground motion will tell about the size of the earthquake and the and also it will tell about the damage, how is the ground shaking was there, and also all these things, and also this three-dimension photo. So we measure the ground motion in three dimensions, and it will give the fault geometry of the earthquake occurred. So for example, see the earthquakes. I already told you the earthquake will. So the seismogram contains. So the seismogram reaches to the station from the different paths, different travel paths. So even though the earthquake is very short-lived phenomena, but the thing is that the seismogram at the station is a very long. For example, 6 magnitude earthquake, the length of the seismogram may be 40 to 1 hour. So because it travels from the different paths and reaches to the station. So the length of the seismogram, what we see at the recording station, is very lengthy. And also how we determine the earthquake parameters. So nowadays we estimate the earthquake parameters from the first motion of the seismic waves. So that is the first arrival of the P waves, the location of the 4 unknowns. So because the unknown parameters are here, this is the latitude, longitude, and the focal depth, and also when the earthquake was occurred. So these are the 4 unknown parameters. So from the 4 locations, from the first measuring the P arrival times only, we can measure this hypocentral parameters. So hypocentral parameters were determined from the at least for 4 stations through use least square method. That is the inverse problem, because we know the output parameters. From output parameters, we have to go into the back calculations to determine the path as well as the source parameters of the earthquake. So in order to measure the stations and this thing, we maintain the networks. Networks. So the networks are seismological network. The seismological networks are divided into 3 categories: local, regional, and global. So in the local network, for example, to monitor the earthquake activity very closely, nowadays it is earthquake activity is going on in Delhi region. So we established, apart from the 7 permanent seismological observatories, we established 9 more seismological observatories to closely monitor the earthquake activity. So here we can monitor the magnitudes from the ranges from down to magnitude 1.5. And regional network, the spacing will be around 150 to 200 kilometers between the stations, which monitor the earthquakes of magnitude 3.5 and above this thing. This is the so what we do in the National Seismological Network is a regional seismological network. And here the data, all the data will come through by dedicated communication link, and the sampling rate will be around 100 SPS like that. And in the case of global earthquakes, which spread complete globally, and they can monitor the earthquakes of magnitude 5.0 and above, and interstation distance is 3 degrees, approximately 300 kilometers, and the sampling rate will be very small because the data will come through by to the stations, to the processing centers through by internet, that is the 20 SPS. So the bandwidth is limited, so the sampling rate will be around 20 SPS or 1 SPS. So this is the I will tell you in the country the network expansion has took place according to the when the major earthquake was occurred, this thing. So after the 1897 Shillong earthquake of magnitude 8.1, and we established the first seismological observatory in Alipur, Kolkata. And 1940 we have 6 observatories, and 1950 8 observatories, and 1960 so we established the 4. Then the concept has come long period and the short period. So long period records, the seismograph will record the, here you can see this is the, which can record the distant earthquakes, and the short period seismograph will record the local earthquake activity. So like that, this is all analog era only. And 1970, we have some, and afterwards in 1999, we established the 10 global seismographic network after the Jabalpur earthquake. And then we started in the year 2000, we had the Delhi telemetry network, and also in 2011 we established the Northeast telemetry network comprising of 20 stations. Now recently we in 2016 and 2018 we added another 78 seismological observatories. So the total network has become now 115 seismological observatories. So this is so now, earlier the digital seismological observatories are operating in the standalone mode. Now the observatories are operating in the continuous. So data will be we receive the data in real time through by VSAT network. So here what are the components of the seismological network? So seismological network is basically consists of the a seismometer, which is the basic building block of the recording station, which measures the ground motions. So in the ground motion, since the ground motion, for example, distant earthquakes is very, very small, it is in the order of few nanometers per second. Whereas when the earthquake happens near to the recording station, then the ground motion is very large. So we have two types of instruments. One is the weak motion, and another one is the strong motion. So the weak motion is called the broadband seismometers, and the strong motion recorders, we call it as accelerometers. Sensor is called accelerometers. So we have the two types of sensor, basically broadband seismometer, which is the measures the weak ground motion in terms of the velocity, and the accelerometer, which measures the ground acceleration. So the ground acceleration will be high only when the earthquake is felt in the region, and that time it will produce the data. So this data will be goes to the data acquisition system. It is a 6-channel, and it is because we measure the arrival times of the seismic waves. So the arrival times of the seismic waves has to be measured very precisely. So even 1 second means the seismic waves will travel with velocity, P wave will travel with velocity 6.5 kilometers per second, and S waves travels with 3.5 kilometers per second. Even if 1 second difference is there in the measurements, so the calculations and the parameter determination will go wrong. So we have to maintain precise timing. For that, we use the GPS timing device. And all these sensors and the digitizers will work from the battery, and then the data will goes to the through VSAT communication through then the real-time data will come into the acquisition system here. So here the acquisition system and the data will be displayed here. The incoming data will be displayed here, and then there is a auto location softwares which continuously monitor the whether any change in the signal to noise ratio of the signal for each station, for each component, and then it will associate that increase in the signal to noise ratios where the signal to noise ratio increased, that where it has got triggered. So the triggers will be associated, and then the parameters will be determined. I will come to the later about that determination and everything. So like this, we have 115 seismological observatories. So all 115 seismological observatories are equipped with the weak motion sensors and strong motion sensor. That means we can record both the very small signals in the range of nanometers per second, and also very large signal in the range of 2G. 2G means approximately 20 meters per second square. So we can measure the strong ground motion as well as the weak ground motion, and all the data will come in real time to the operational center. So mostly we have I will come to the, so operational capability with this network is more or less it is 3.0 and above. And at present, apart from that, when there is a very spurt in seismic activity, when there is an increase in seismic activity in particular areas, then so it is the regional seismological network cannot monitor those very small earthquakes. So that time we go to this affected area and install the seismological observatory, temporary seismological observatories, and they get the data and record the data. So all this, for example, if the earthquakes are very shallow focus and focal depth is very small, then the most of the energy will come to the surface, and then it gives rise to one kind of a rumbling sound. Though magnitude is very small, since focal depth is small, it is in the shallow focus. Then it is given rise. It gives rise to a rumbling sound and felt locally. So it creates a panic among the people. So that time, and when we observe such kind of activity in any part of the country, so we deploy the temporary seismological stations to monitor such activity. And also, since our network capabilities, we have to enhance our network capabilities and dissemination capabilities, and we are continuously striving hard to, as our director told, informed to the members and panelists, so that we are continuously striving for the strengthening our the National Seismological Networks, and also we are going to add 300 more stations in next 2 to 3 years as a building block for the earthquake early warning system. So this is the operational capability of the National Seismological Network. We can record any earthquake of magnitude 3.0 in Peninsular Shield region. And for example, see 3.0 earthquake means the seismic signal can go up to from the source region to up to 250 kilometers. So if we should have, when the source is there within the 250 kilometers, we should have at least 5 stations. Then only we can determine the earthquake parameters reliably. So our interstation is about 220 to 250. So we can fairly monitor the earthquake activity of magnitude 3.0 and above. But sometimes the instruments may give the problems. That time we have the problems. We cannot locate such earthquakes. And also in the Andaman Nicobar Islands, we can monitor the earthquake activity 3.0 and above. Since we INCOIS has also established some network there. And also extra peninsular region, we have observatory. We can monitor the earthquake of magnitude 3.0 and above, and 3.5 in the border regions of the country. In the Delhi and surrounding region, we have very strong network. Earlier, we are all with 16 station, and and 9 more stations we added. So within the 200-300 kilometer radius, now we have the about 20 stations around the Delhi. And also after this spurt in seismic activity in the Delhi region in the month of April, we established some more 9 more temporary seismological observatories in the Delhi region. So this is, and also in the northeast India, we have about 21 seismological observatories in the northeast part of the country. We can monitor fairly any earthquake of magnitude 3.0 and above. So, and also any earthquake of magnitude, since we get the data from the international stations also, so we can monitor any earthquake of magnitude 6.0 in any part of the world, this thing, and also we can tell to the and data will go simultaneously to our data will also go simultaneously to the INCOIS for the tsunami warning purpose also. They can use it for tsunami warning purpose. So this is the seismological operations. So since the earthquake doesn't have the boundaries, it is a global phenomena. So we get the data from the global stations also, from more than 100 global stations. Data will also come through the internet to our servers. And also we have the exclusively real-time seismic monitoring network 17 stations, but and also 17 stations, and recently we had 78 stations, and data from the other universities, and this thing we also get 28 seismological data from the other national institutes. And also we get we have the northeast telemetry network of 20 stations. All the data, about 20 GB of data in real time, will go into will come into our central processing center at Delhi, and data will go simultaneously to the INCOIS Hyderabad also. So this is our this thing, and all the data in the fly will be converted into a standard format called the seed format, because because we have the different type of seismic instrumentation manufactured by the various manufacturers. So each manufacturer uses its own data format. So So that is that data format has to be converted into a standard format. We convert all the data into the seed format and fed to the auto location software. So I will come to the later about this. So since uh, as our director earlier told that till the technology has not at the scientific technique, the world has not reached to that level to predict the earthquakes correctly with respect to the time of occurrence, magnitude, um, and the region, and it is still in the primitive stage. And warning is not so. Only timely dissemination of earthquake information plays a very important role in the post disaster relief and rehabilitation. So this is the main mandate of our National Center for Seismology. So we disseminate the earthquake information in the least possible time within the 2 to 3 minutes after the occurrence of the earthquake. So the operational task of the National Center for Seismology is to get the data from all those stations and then and look for any earthquake activity in the region and also in the other parts of the world. So this is the you can see here it is the real-time data is coming from the different stations, Agartala, Ajmer, Akola, and this thing. And you can see that the red this thing. This is the triggers. So the software has thought that there is a trigger is there. The trigger will happen when the signal to noise ratio will exceed some level. Means that is the user defined this thing. So it is different from the for each station, and when the threshold increases, then the software thinks that there is an earthquake has happened in that recorded by the station. So when the at least this software will associate such triggers more than 10, or 10 or more, and think that and immediately it will based upon that trigger, it thinks that P has arrived at that station and determine the auto location parameters. So this auto location parameter, then it flash it on the our website and our mobile app, and also it will be informed through SMS in our MOS officials and NCS officials. So this is the first cast parameters which have been determined from the 10 or more stations, uh, 10 or more stations, and it is done automatically. So means that is from the initial part of from the initial part of the seismic waveform. So initial part of the seismic waveform may be about yes.
Yeah, due to time constraint, I request you to conclude your PPT in 2 minutes.
It's a very short time. So this is the associate, and the earthquake parameters determined through by automatic analysis may not be sometimes may not be reliable, and it may prone to the error. It may prone to errors, and that we call it as a false event. So we are improving upon that. So it is not only it is not for the for our National Seismological Network. It is for other national networks, National Seismological Network maintained by the other parts of the world. So this is the our this thing. Soon after the earthquake, within the we publish the earthquake information on the website and mobile app. Our mobile app is the RISE, RISEQ. I will come to that one. I request all the participants to download this mobile app and give your feedback, and go and you can look into the more details on the earthquake information and the other value-added products. So, and then after the scrutiny, because the first level information is may not be correct, and this thing, and the duty officer will scrutinize those parameters and disseminate the information to all the nodal officers and decision making authorities and this thing. So this is we are improving upon the our this thing. Earlier we used to take in 1996, and this thing we used to take when analog observatories are there. We get the data from the telegram, and this thing. That time we are take 1 hour for dissemination of this information, and now we are able to disseminate the information from the 5 to 8 minutes this thing. So this is the our National Center for Seismology's website. It has the complete information about the event occurred, and also it gives the intensity of the earthquake, how the earthquake was felt in the different areas, that information also will be there, and also you can submit the how the earthquake was felt in your area. That did you feel it option is also there. So apart from it, we publish the how the faulting was occurred, and then all the value added products, those things, past seismicity, everything will be available in the this thing in our website. And also you can download the all the past data from our website, and also we can make a request for the waveform data also. This is our RISE queue. This thing is our mobile app, so you can download it, and also you submit your feedbacks for improvisation, and a lot of information will be available in this mobile app and our website. This is the seismicity of our Indian region. And so this is a magnitude 5.0. So mostly seismicity is concentrated towards the collision zone, and this is the here the and the subduction zone and the intraplate seismicity. So okay, I will conclude it very fast. So this is the recently we have the earthquake activity in the Delhi region, and we have recorded several 20 to 25 earthquakes, more than 25 earthquakes in the Delhi region, and it was felt widely also. That this is in the northeast Delhi border and Rohtak area, and 17 kilometers east of Faridabad, and this is the this thing. The maximum magnitude of the earthquake is 4.5, which was occurred on 29th May. This is the how the earthquakes are happening in the Delhi region itself. And as per this thing, for 4 to 5 years, then an earthquake of magnitude 4 and above, this general pattern in Delhi adjoining area, magnitude 4 and above will takes place within every 4 to 5 years, once in 4 years. So this is also another activity is going on in the this is the Kerala also, Idukki also. We are monitoring very closely, and then I have given in Polgar also we are monitoring the earthquake activity, and this is the northeast region, and now there was a earthquake of magnitude 5.9 in so the, in Mizoram district of so. We are this is the this is mainly the seismicity is attributed to the Kopli fault, and Belonia, and all the our Dubri fault and the Dauki fault, all those things. We are continuously monitoring the earthquake activity in that area. And also I will talk about the due to time constraint and this thing, I will skip this early warning system and earthquake early warning. And we are I will just talk about our future activities. We are enhancing our upgrading our seismological network from 115 to 150, and also we are enhancing our we are with more value added information on the earthquake dissemination, improving our dissemination capabilities. And also we are going for the addition of 300 more new seismological observatories in the near in 2 to 3 years. And we are and also we are going to take up in future about earthquake early warning system also. Thank you very much for this.
Thank you, sir, for providing insight on importance of seismology in providing information of earthquake like location, magnitude, and also the seismological network established across the country and future interventions of NCS. Our first speaker provided glimpse of seismicity monitoring. Now the second expert will touch the engineering aspect to manage the impacts of earthquake. And for that, I will invite Professor Ravi Sinha from IIT Bombay. Professor Sinha is closely associated with policy making related to disaster risk management. His research work is mainly in structural engineering, specializing in earthquake engineering and disaster risk management. Professor Sinha has chaired and served in several government panels. Professor Sinha is also a member of Maharashtra State Disaster Management Authority. Over to you, sir.
Thank you. First of all, I would again like to echo my previous speaker in thanking NIDM for organizing a series of extremely useful webinars covering a whole range of topics of relevance today. And I really look forward to NIDM continuing to build on this momentum and being able to contribute more effectively in disaster risk management in India. What I'm going to talk to you today is building on what Suresh has already presented regarding understanding of earthquake, and then based on that, how do we manage the earthquake? And for that, how do we convert the information we get into something which is more tangible and which is more actionable? And I would show you some of the things which have to be done for that, and exactly what are the what all has been done. So I'll give you one example of that particular effort. So first of all, if you look at earthquake risk management, then obviously it has to be science and knowledge based. It cannot be on the basis of perception. It must be on the basis of knowledge and backed by good science. And you should take into account, obviously, the present ground realities. One of the ground realities is the ability to get the information accurately and in time. Then the future growth trajectory. This is important because there is a linkage between disasters and the impact on economy and impact on the people's well-being, which goes far beyond the people who are directly affected by the disaster. And lastly, the aspirations of the at-risk people. The threshold of people's ability to absorb disasters or losses changes with place and also changes with time. So disaster risk management has to take this into account in order to be effective. Then obviously the risk management has to be compliant with the relevant laws and rules, should conform to international standards. We are now a major international player. We cannot take steps which make us into a laughing stock. We need to stand up to our reputation and our prestige. It should take into account governance and institutional capacity. And these are obviously locally owned, so they have to be at the local level. And then the strategy should be implementable and sustainable so that they can be mainstreamed. So if I look at earthquake risk, the information which are needed in order to do risk management, first of all is that we need the information on hazard, the very first box on the top. And this essentially tells you about the strength of ground shaking. Then we need information about vulnerability. What is the impact of that ground shaking? And this is primarily the impact on structures, because it's the structure damage or the shaking of the structure which results in the adverse consequences. And then we need information about the exposure. So if structures are damaged, then what is the impact of that damage? There may be direct losses in terms of, say, the repair cost and so on. There may be indirect losses, factories being shut down, government departments being closed, hospitals not able to treat patients and so on. And in every case of the losses, there would be a social loss, the number of casualties or the number of people affected and so on, or the number of government departments which have become dysfunctional, and the financial loss, which is more in terms of the repair and the restoration cost. And all of them together will give us risk. So when we do risk management, basically in all those three rectangles, we can take steps to reduce the consequences. And it is not that there's a linear process that we have to do one before we do the other. Simultaneously, we can tackle initiatives in all three of these boxes. So if I look at the hazard, then it can be the understanding of the hazard can be based on the knowledge of past earthquakes. It can be based on understanding of the current seismic activities. And my previous speaker had just given a very good summary of what is currently happening in the country on this. And it can also combine the current understanding as well as the historical knowledge to get a better understanding of the hazard. The vulnerability depends on the type of building stocks and their specific vulnerability. How strong are each of these building stocks? Depends on things like material of construction, architectural features of the buildings, the structural systems, a number of technical things. Then exposure, both the impact and resilience, so the ability of the people to absorb losses can be incorporated. And we typically consider both the social or the human losses as well as the financial losses when we are looking at exposure. One of the things about exposure is that by understanding exposure, various government agencies, various departments, various other non-government stakeholders, they can assess their ability to fulfill their expected responsibilities in the event of a disaster. So to take one example, so let us say there is a particular kind of event which occurs somewhere near Delhi and which affects Delhi badly. This particular step over here, we can have the hospitals look at their ability to continue to function if the event occurs. So are they of the strength and are they of the kind of equipments which they use that they will be undamaged, or will they be slightly damaged, or will they be significantly damaged? So they can assess these things in advance and then decide whether they need to take some remedial measures or not. Then also particularly relevant for government departments is that they can use this information to assess the effectiveness of their risk management measures. So if a particular ministry's disaster management plan, is it geared to be able to continue to function when this kind of an earthquake occurs? So we have had many examples in the past in India and also in other countries where after a major earthquake, the ability of the government to effectively manage in the short term was badly impeded because the government officers were busy taking care of the needs of their own families and their own communities. And these are very, very real conflict between the need to manage the casualties within the family and the need to manage the responsibility imposed as a government servant. And there is no clear answer on how to manage these things. So obviously, having this understanding beforehand and then planning for it is useful. And another thing is that earthquakes cannot be managed by just one or two government departments. It has to involve many, many stakeholders together. So it requires coordination between the stakeholders, and that would also require understanding whether the coordination is functional or not. And this can also be done by understanding the exposure step. So all of these can be done and are being done to various levels of efficiency in state governments and in central government. So earthquake risk will combine hazard, vulnerability, and exposure. And one thing we have to keep in mind is that risk can change with time and does change with time. So one of the things which changes with time is the people's what you can call as the risk threshold. As India becomes more and more, say, economically advanced, people's acceptance of risk reduces. And this is not just in India, that this is something which happens in all the countries. And because of that, the risk management strategies which have to be implemented also has to gear up to meet the people's expectations. And one of the most useful way in which these can be done is through developing scenarios of earthquake events. So take scientifically valid and based on very clear scientific information, a certain earthquake event and map out what is the consequence of the earthquake everywhere. And it provides a lot of useful information. For example, we are able to de-aggregate the risk, which means that we are able to find out how much of the risk is because of the strength of shaking, how much of the risk is because of the impact of the shaking on different kinds of buildings, how much of that is because of the institutional setup of different government departments and so on. And also we can see what is required to manage, where are the resources available for that, and obviously resources are never sufficient. So then how do we prioritize? And these things can be done in advance and planned. And one thing I would like to caution is that simplistic risk management approach is rarely effective. I mean, this has been shown in the country time and time again. It has been shown in other countries also, that if we feel that common sense is what is going to save us from the adverse effects of an earthquake, then unfortunately, so far, we have not even have a single evidence of that being true. So this is showing the earthquakes which have occurred in and around India during the last 100 years. There was another similar figure shown earlier. And what you can see is that pretty much no part of the country is untouched from the shaking of an earthquake. So the dots represent the epicenters, but obviously the shaking is also experienced far away from the dot. So no, I mean, it doesn't matter where you are in the country. you cannot say that earthquake is not something which I should take care of. Obviously, earthquake risk management is required all over the country. This is an interesting study which showed what are known as the seismic gaps in the Himalayas. So in the Himalayan region, which are known to have very large earthquakes occurring periodically, there are certain areas where earthquakes have not occurred in the last few hundred years. And there's a hypothesis that these are the areas where a large earthquake may occur soon in the near future. And why it is important is that if those earthquakes occur, then the region around these gaps where the shaking would be very strong, those are the areas where the earthquake risk management effort has to be particularly taken care of. So I will show you the scenario of a magnitude 8 earthquake in one of those gaps, and it's actually a recurrence of an earthquake which had occurred in 1905, so known as the Mandi earthquake, and it is occurring in a seismic gap where a very large earthquake has not occurred in the recent past. So if I go back to this, you can see that there is a black dot on the top showing 1905. This is a Kangra earthquake, and just to the right of it, there is a gap, a white one, where an earthquake has not occurred for nearly 600 years. So if the 1905 earthquake approximately reoccurs, and there is no reason why it cannot reoccur, can reoccur in this gap, which is an extension of the same fault area, same fault planes, then what would be the consequence? So this is showing the area in closer. There are a lot of lines being shown in blue. Those are the seismic faults in the region. There is a dot showing Kangra. There's another dot showing Shimla. And the location of the earthquake is being shown by a star. And Chandigarh also you can see in this map. And this is another picture again, removing the other seismic faults, only showing the fault which has ruptured. You can see a blue line. The blue line represents the length of the fault where there is a movement which takes place when this magnitude 8 earthquake would occur. And again, you can see all the districts. The districts to be affected belong to Himachal Pradesh, Punjab, Haryana, and also partly in Uttarakhand and partly in Jammu and Kashmir. And the Union Territory of Chandigarh is also within the strong shaking area. This is again showing the faults further close up. Many of you are from this part of the country. I saw in the blogs, lots of people are from this part. So you can more closely locate to where you are on the basis of this hypothetical earthquake. So this is again showing a cleaner image that if you have the rupture, then the rupture corresponds to the blue line. So you may have a very strong shaking even far away from epicenter, because the earthquake rupture may be very close to you, even though the epicenter is not that close. So for example, Mandi district is likely to be badly affected in this particular hypothetical earthquake because of the fact that the rupture extends all the way up to Mandi, even though the epicenter was far away. So how do we assess damage? The way Indian decision to assess damage is through what is known as the earthquake intensity, divided into 12 intensities from 1 to 12. 12 is the strongest earthquake intensity, where there would be large-scale landscape changes. 11 is where there is large-scale destruction, including very, very large cracks in the ground and so on. And then 10 is when most of the well-built buildings will suffer irreparable damage. So even if they don't collapse, they cannot be repaired. 9 corresponds to well-built buildings suffering extensive damage. So obviously buildings which are not well-built would be performing much worse than this. 8 would be when most of the well-built buildings will suffer damage, but not so much collapse. 7 corresponds to damage to buildings where many of the buildings will suffer moderate damage. Major damage would be only a few. And then you go to lower and lower intensity of damage. And in this particular earthquake scenario, now I'm showing you contour maps with different colors. The darker the color, the stronger is the damage intensity. And what you can see is that near the epicenter and the surrounding area, the damage intensity is somewhere around 9 to 10, which means that even well-built buildings which are complying with the Indian standards are likely to be badly damaged or almost on the threshold of collapse. And then the next outer ring is the damage intensity 8 to 9, which represents well-built buildings suffering extensive damage or major damage. And then further out, as you move further and further away, the extent of damage gets less and less. But what is important over here is to see and realize that that there are regions where the damage is going to be so intense that even if the building is well built, it is likely to be experiencing major damage. So which means the use of those buildings are not likely to be available unless those buildings are repaired in the months or years to come. And that is for the well-built buildings. So the lesser built buildings would suffer even more damage. So this kind of information just on the shaking itself is not giving enough really information to the government departments to decide what to do. And that is why those other steps become important. So in the case of this earthquake, for example, the area of the different shaking I have shown over here. Himachal Pradesh I have shown separately on the right because this epicenter, this hypothetical epicenter has been taken in HP. But you can see that Punjab, Haryana, Himachal, and Chandigarh together, what is the area in square kilometers for each of those damaged regions. And we can actually map out the population on it. So this is the population density as per the 2011 census. And you can see that those black contour lines were those damage intensities of 9, 10, 8, 9, and so on. And you can see that there are many areas which have very high population density, which are in the very strong shaking region. And if you look at the population, so 23 so 2 million people or 2.3 crore people are residing in the intensity 9 to 10. So these are the areas where a large fraction of the buildings are going to be severely damaged. Now this starts providing information on what the government should be doing, or what the what the people should be doing to save themselves, for example. So what we are seeing is that a large earthquake can cause a major disaster as it adversely impacts the people, their built environment, and the region at large. And the risk management, it considers the impact of the event in terms of the potential damage and losses before they have occurred. And what we have to keep in mind is that disaster risk management can only be effective if the risk in terms of damage and loss is understood before attempting to manage it. If we just understand the shaking, for example, that may not create enough momentum to decide where to spend how much money in managing it. It's a very important step to understand the shaking, and then we have to use it to move forward and also overlay the other information which we need. So scientifically rigorous scenario helps to make the disaster believable, and this is required for active participation of the stakeholder agencies. So there have been many cases in the past where there have been PILs, and the government has answered saying that they need credible information in order to do budgeting. And credible information requires that they need to know what are the consequences and where how much money has to be spent. And those are valuable and valid needs of governance. So the disaster risk management strategy has to be able to support that. And that basically requires the agencies should be able to understand the specific causes which lead to various consequences. And unless they are able to understand that, it becomes very difficult for them to act on it. And this kind of a scenario development project, we believe, so this one which I have shown was taken up by the National Disaster Management Authority in partnership with IIT Bombay some time ago. And this kind of a development plan should be taken up all over the country, particularly in areas which are highly prone to large earthquakes as part of long-term mitigation programs. And the information which you get out of this actually have been used and in future can be used for various programs of the government departments for risk mitigation, for risk reduction, for preparedness of residual risk. So after you have carried out the mitigation and reduction, you cannot 100% eliminate the risk. So you still have to manage the residual risk to decide on the size and the capabilities of the search and rescue systems, for on the response systems in terms of, say, emergency response, emergency shelter, emergency medical requirement, and so on. So all of them can be mapped to scenarios on the basis of which risk management plan can be decided. So I would just like to wrap up over here by saying that we need to understand the earthquake hazard, we need to understand the consequences of the earthquake, and we need to put it all together by mapping what are the responsibilities of the various agencies and how the agencies would be able to meet these requirements. Thank you very much.
Thank you, sir, for highlighting this concept of the different elements that should be incorporated in earthquake risk management strategies, calculating the consequences of earthquake and components to manage them, like effective coordination of different stakeholders. The third and last expert of today's technical session is Professor Surya Prakash from National Institute of Disaster Management. He is currently head of Geometeorological Risk Management Division and faculty in charge of 3 specialized centers: Center for Hill Area Development, Early Warning Communication, and Center for Coastal Disaster Risk Reduction. He is also coordinating faculty of 8 central ministries: Mine, Communication, Northeastern States, Petroleum, Natural Gas, Shipping, Labor and Employment, New and Renewable Energy, and Parliamentary Affairs. Over to you, sir.
Anil, am I audible?
Yes, sir, you are audible.
My PowerPoint is visible?
Yes, sir, your PowerPoint is visible.
Okay. Okay, friends, my former speakers, they have talked about earthquake monitoring and also what are the lessons that we have learned and scenario creation of a worst case scenario for a maximum probable earthquake in any particular area based on historical earthquake data. Now I'll go to some of these slides which are been put up for awareness about earthquake. A general awareness is needed because if you know the things, you can prepare against them or you can act against them properly. So first thing is that why do these earthquakes happen? In a general sense, we call them as ground shaking because of endogenic processes. And one of the regions that is cited for the cause of earthquake is plate tectonics. That earthquake is divided into different number of plates, and we need to make our public, the one who is the major stakeholder, aware about this structure of the earth. And this can be done through various models which has been projected in various places by other people. And there are about 20 plates. 8 are almost major plates, continental plates, and other are mix of continental and oceanic plates. And this is how they have distributed. These arrows actually are showing you the different direction into which these plates have been continuously moving. And during these movements, they are either converging towards each other, diverging from each other, or they are moving parallel to each other. So these are the dimensional models which are actually projecting the movement of these plates. And now, because of the force which is actually making them move is the structure of the earth, below the crustal part, there is an asthenosphere, which is part of the upper mantle and which is actually viscous in nature, which generates convection currents and makes these plates move. And this figure is actually showing you them. And this can also be shown through different three-dimensional models in a laboratory or museum. Another important parameter, we are often talking about epicenter. Epicenter is actually not the point from where the earthquake generates. It's actually the point which is lying on the ground and below which there is a focus from where the earthquake gets generated. If the focus is deep, then there may not be much effects of the earthquake. But if it is superficial, then the earthquake will have larger impact. So focus is very important in terms of earthquake location. And when the earthquake waves get generated, it travels throughout the earth. However, there are different types of waves which have different nature and can travel through different type of media. We have, broadly, I can tell you about primary and secondary waves. Primary waves are like longitudinal waves and secondary are like light waves, and they can not travel, the primary waves cannot travel through liquid media. And as part of the outer core, which is liquid in nature, the primary waves will not actually be transmitted, and you may not be able to observe them, while the secondary waves can pass but get refracted. So there are different zones, and these are the kind of waves. Now, just to show you how these waves travel on the Earth surface or within the Earth. So there are the surface waves and the body waves, which come in terms of primary and secondary waves. And if you see them, the surface waves are the most destructive waves which cause damage to our structures. And these are defined in two ways, Rayleigh and Love waves. And Love waves are actually the ground horizontal ellipsoidal waves which cause more damage to the building because of torsional effects. And one more parameter which should be very clear in the minds of the people is magnitude versus intensity. Professor Sina has just told you about intensity, which is actually the modified Mercalli-Sponier-Carnick scale, which is being used. We have two types of scales, but it's modified Mercalli scale, but it's Sponier-Carnick scale. So these are intensity scale, but Richter scale is a magnitude scale, and currently the professionals are using moment magnitude scale. So these are different. So magnitude is actually showing you the energy released during the earthquake, like the wattage of a bulb, and the intensity is actually the illumination of that bulb, which can decrease with the distance from the earthquake source. That's why you could see different. And the advantage that we are taking in terms of earthquake early warning is the time gap between the primary and the secondary waves because of the change in velocity. So the velocity of the primary waves is faster, whereas secondary waves travel with lesser, so it takes more time. So you can get a time gap which can help us in early warning. Now this is the seismic duration map which has been already shown, and these are some of the recent earthquakes. My experience is started long back in 1991, earthquake on 20th October, when I was working for a landslide to save an ITBP camp in Uttarkashi district. And suddenly we had an earthquake in the Uttarkashi district. Being part of the Department of Earth Sciences at IIT Roorkee, we were supposed to give the information where the seismograph was placed. So the information was sent to the DM, and thereafter the actions were taken. Currently, the NDMA, the first guideline to my best of knowledge were on earthquake. That was given a priority. And the guidelines on landslides and earthquakes are very much interrelated. And not only working within the country, but also we were working regionally. Because earthquake not only within the country, but across the borders can also affect our territories. So we had held East Asia Summit for earthquake risk reduction in 2012. We had a virtual knowledge center as part of that ERR, and 24/7 point of contact for the 18 countries, including the 10 ASEAN countries. And as part of our national initiatives for national platform on disaster risk reduction, we had also carried out sessions on earthquake, special sessions. And you can see Dr. P.K. Mishra is present in this, who had actually dealt with the Gujarat earthquake in 2001. He was the one who had actually dealt with it. After the Sendai framework in 2015, we had gone for Asia Ministerial Conference, recognizing the need for international collaboration for managing such major disasters. Now I come to our local levels. In Sikkim area, we had faced a major earthquake on 18th September 2011, when an earthquake of magnitude 6.8 struck. And this was a Sunday evening, and on the evening, I could personally feel the earthquake while sitting at Delhi. That was the intensity of the tremor and the distance traveled by the tremor. And this is the situation in the Gangtok area, where, or the Sikkim, I can say, because Mangan, North Sikkim was the epicenter, and Gangtok also got very much affected by this earthquake. Now, one of the buildings of a civil engineer, which itself got affected, and the lower part of the buildings had low columns, so therefore the building's ground floor has suffered damages because of this earthquake. Now, oftenly we say that the adobe buildings or the poorly constructed brick masonry buildings may face more damages, or the boulder masonry buildings may face more damages. But you can see a recently constructed reinforced RCC building also failed during this earthquake. So several such instances we have recorded, not only from the Sikkim earthquake, but also right from the Uttarkashi earthquake in 1991. Almost every 2 years we had faced one or the other earthquake and seen the similar instances of the damages. I'm showing one of those cases here. You can see all the floors get collapsed despite steel bars of almost 16 mm thickness. They have almost collapsed like a pancake failure, and this has been happening, and this has to be actually properly analyzed. What are the deficiencies in our design, construction, or implementation? And this kind of scenario actually happened in the Sikkim earthquake, and the parapets and the staircases also got affected very much, being the ancillary parts of a building construction. So these kind of field features, you can see not only the collapse of the structures, but also the bending, the torsional bending in a very bad manner of very thick steel bars also was the result of the collapse pressure on the columns and the bars. Now, coming from the buildings to the pilgrimage places like Buddhist place, that place, Mutt, that also got suffered from the damages because of this earthquake. The temple also got, you can see the top of the temple is off the there because of the damage by the earthquake. And this was a church area, which all those, whether church or temple or a mosque or a mutt, all got affected. This is very old mutt, which was there for hundreds of years, also got affected by the earthquake in 2013. And these buildings, you can see, they're constructed with the stones and mud materials, which actually are not very much resistant or absorbing the shocks or the tremors. Rather, they get weak and they fall down and cause the damages and can even casualties. Not only the private buildings, but also government buildings. You can see the secretariat buildings. It suffered heavily during the Sikkim earthquake. And now I come to, we openly think when we are creating the scenario or designing and planning, particularly for the hill areas. Professor Sina talked about the Kangra earthquake 1905. Actually, the major problems are not just structural problems, but also the slope stability problems. Most of the slopes during the earthquake becomes active, and they either reactivate or new landslides take place. And the buildings located over them also fail because of failure of the slopes, not because of the failure of the building. You can see all of the buildings slided down in the Sikkim earthquake, and it is falling down over the slope because of the slope failure. So these kind of things has to be actually examined properly, that wherever earthquakes are taking place in the hills, these are not only the structural problems, but also the slope stability problems and the infrastructure problem. The water supply lines break down because we are providing rigid pipelines, not the flexible pipelines for earthquake and landslide prone areas in such areas. And even the press and the media buildings also got affected. And all the highways, we cannot access those people. I was part of the team which went for documentation immediately after the Sikkim earthquake. And I remember that the weather was so bad that we could not even fly. And the roads were completely blocked. We could not access those areas of the North Sikkim part, like Chukuntham, Lamchen, and other areas which were very affected. So how to provide help to those people? And we have to always consider these kind of problems which are also associated. When we dealt with the earthquake in Nepal on 25th April 2015, we also dealt with landslides, and we took care of them because we had learned lessons before that, that there were instances of several landslides in the hills, which do happen along with earthquake. And some of the tribe people also tried to manage. And rockfall is one of the most common landslides that take place. Now I take you from our national scenario to international. I happen to have experiences from other countries on earthquake besides the earthquakes experience in India, and this was in Turkey. And you can see most of the housing buildings in a remote village area actually came together along with the slope getting moved. And all these buildings moved together. And the building structures, what we have in India, were similar to that. The stone masonry buildings, the brick masonry, and the hybrid buildings. That you can see the ground floor is stone masonry and the upper story is brick masonry. So such kind of hybrid structures actually are not able to harmonize the impact of the earthquake and fail. Collapsed school buildings. You can see even the stone machinery buildings with different types of stones do fail and develop cracks. And this was lucky chance that the earthquake happened in the early morning that school was not open. And this is another school building. You can see the whole of the building got collapsed. And this was the inside scenario. The wall fell inside the building. So if the children were there, they would have been a victim of such an earthquake. So particularly a hospital, educational and health building where we have put emphasis in this Sendai framework also have to be well taken care. And all the furniture was getting broken due to this. Another important, often we think that adobe structures can bear the impacts of the earthquake. This was an earthquake of a magnitude about 6. And adobe structures did fail in this manner. And they were using the carpet blocks. Carpet was like, cow dung and other things. They make brick-like structures and use them along with the stone and use mud as a masonry material, and that they think can absorb the shocks, but did fail. Cylinder-like structures, big, long, have larger impacts of the earthquake compared to other buildings. Similar, the earthquakes were held in other areas like China. The chance to visit those areas which happened to be affected, and they were harshly affected by this. Tension was talked about before ancient in 1975, when which was predicted. This went unpredicted and caused heavy casualties. So now these Wenchuan, these kind of buildings in the hilly terrain, they got affected, and the new constructions were well built in the same area. However, the old structures which were affected but preserved so that people can learn, and this was made a learning museum, field museum for the people to learn from the impacts of the earthquake and how these impacts were maintained using reinforcement structure. 350 fatalities in a school happened during this earthquake. Almost 20% of the fatalities were because of the landslides, and faults were marked in the field, and the people's memories were kept on the boards so that they should not forget their near and dear ones who became a victim of the earthquake. And the torsional forces of the earthquake that can bend the girders, railway girders, the tracks also were kept preserved and national memorials. And this was from Taiwan. Another earthquake which took place in 1999. Turkey also had a 1999 earthquake, and Taiwan had on 21st September, and they kept all, even the watches and the other materials. Again, we come back to the memorials of 12th May 2008 Wenchuan earthquake or Sichuan earthquake, and they built experience center for people to learn that how would they feel if an earthquake of this intensity happens. And this is again another school building which got affected and was preserved to show that how these buildings can get affected and children can become victims, and kept, and memorial parks were created. And even in Taiwan also, similarly in Japan, we were having a partnership with Japan and a collaboration. And 11th March 2011, the team of the earthquake experts went from India back to their place in Fukushima area, and this was the result of the earthquake-related tsunami. And this happened in our country also in Indian Ocean on 26 December 2004. And not only the tsunami displaces the materials and the buildings of the vehicles, but also causes fires. And this happened case of triple junction when the Indian plate was submerging in the under the Sunda trench under the Burmese plate and the 2015 earthquake. Another issue which I wanted to highlight through this presentation is landslide dam lake. Not only the landslides happen and block the road, but also block the rivers. And that river forms transitory dams and lakes, which can again cause subsequent floods. So there are interrelated problems that had happened. Kaligandaki river was actually blocked on 24, and the major players, everyone has to be a partner in this process, whether architects, builders, contractors, designers, financiers, government servants, officials, homeowners, and all individuals. Until unless every individual is well aware about it, we cannot do. And interinstitutional cooperations and intercountry cooperation, international cooperations are required. And we have to have shake tables to test our designs and constructions and structures like the one which we witnessed in Public Works Research Institute in Cuba, Japan, and in Macedonia. There are a number of such shake tables available in various countries, which we also have, and also learn from our traditional wisdom. I remember when we were working for the earthquake reconstruction and rehabilitation in 1991, after the Uttarkashi earthquake, the World Bank sponsored project and provided funds. And that time it was UP, and we found several structures which actually did not suffer and which were very old. And one of them was the Firol in Rathal village and many other such structures which were traditionally constructed. And they not only registered the damaging forces of the 1991 earthquake, but also they were older and resisted the forces of 1803 Garhwal earthquake also. For the public and community awareness, we have to have a pocket guidelines for earthquake emergency preparedness and survival skills, and also make them practice through mock drills and exercises, drop cover and hold. And then there are some things about myths to be removed and information to be provided to public about earthquake early warning through animal and birds behavior. There is some scientific data which is available about different types of animals and birds, how they feel about primary waves of the earthquake and their reactions, and at what distances, and what will be the nature of their behavior before an earthquake happens. They do react to weather conditions also, so we have to distinguish with that. And I can, because of shortage of time, I will not be able to read out everything. We can share this presentation and you can learn, and most of these information are available on the net also. Then do's and don'ts available through the RiseCube app also, provided by our National Center for Seismology. It is available on NIDM website as well, NIDM.gov.in, and we have a self-study program on earthquake risk reduction, that is NIDMSSP.in, and there are earthquake risk reduction program with World Bank Institute that we had, that is online NIDM.gov.in. And Japan is one country which had a lot of earthquake. Circum-Pacific belt is the one which has almost more than 85% of the earthquakes happening over the globe. So these they are preparing against tsunami, earthquake, landslides, floods together, and put the stone and a crossroad to make the society resilient against the disasters. You move it in any direction, it will quickly regain its position. So they say disaster may come and go, but we should be resilient to recover at the earliest possible. This is my last slide. Any questions? I will welcome. Thank you very much. Thank you, Anil.
Thank you, sir, for sharing your experiences, national initiatives for earthquake management, as well as multi-hazard aspects of earthquake, like producing tsunami, landslide. Lack of appropriate awareness is also one of the cause of casualties during earthquake. We need to enhance the capacity of local communities through awareness generation program, emphasizing the implementation of building bylaws, mock drills, as regarding the earthquake disaster. Now we will take few questions from the participants. And the first question is for Dr. Suresh. As you are aware, Jammu and Kashmir falls in seismic zone 5. However, to the best of my knowledge, we have only one seismograph located in Srinagar, while at least three are required for triangulation of the epicenter. Is there any program for increasing the number of seismographs in J&K?
Yes, you are right. We have the three observatories. One is Leh, Alchi, and another is at Srinagar and Jammu. We have four observatories there. And we are increasing the strength in the next year. We are proposing 35 new observatories in the coming period. So some observatories will be installed in the J&K.
Thank you very much, sir.
In addition to that, I must say that there are 8 observatories working in project mode with Jammu University.
Thank you very much, sir. Our next question is to Professor Ravi Sinha. How to calculate the total damage of earthquake? And are we using remote sensing techniques for study and predicting risk?
In the case of earthquake risk, remote sensing has very limited applications. It does help us understand, for example, which areas are having population and the buildings and all. But other than that, remote sensing as a tool is not very useful for earthquake risk management. There are others which are far more useful. So the best tools are being used. In terms of how to assess risk, so it is a combination of the hazard, the probability of ground shaking being strong in the area, the kind of built environment we have, the kind of buildings we have, the bridges, the infrastructure in terms of their strength, and then also what is the impact of the damage over there. So all of them are taken into account to determine the risk in that area so that the risk management efforts can be taken up.
Thank you very much, sir. And last question is for Professor Surya Prakash. What will be the role of local community in reducing the risk of earthquake?
Thank you, Anilji. Actually, local community is the major stakeholder amongst all other stakeholders because it's the people's buildings which get more affected than the other buildings. So people have to learn to construct their buildings at the appropriate place, particularly when we are in the hilly terrains or in the coastal sites, which are mostly affected either by tsunami or by landslide, which are concurrent disasters along with earthquakes. The second is there are traditional wisdoms, local materials and skills available. What I've seen in Uttarakhand, particularly, if I say in contrast of a post Uttarkashi earthquake, that the machines from the plains are going to the hills and they are constructing brick masonry buildings with flat roofs without considering the earthquake vulnerabilities and proneness. So the old machines and traditional constructions in Uttarakhand were quite good and the damages were less. So communities actually should learn where to construct, how to construct, what kind of material should be utilized, and then also prepare against the remnant risks. Despite all our best efforts, we have to have an evacuation plan. We have to have a safe shelter plan. We have to have a safe evacuation route also. So everything should be known to people that in case I get trapped, what to do, what not to do. And in case I am going to buy a plot and construct a new building, then what kind of provision should I follow? That is most important. And particularly while building on slopes, the slope stability consideration should also be there.
Thank you very much, sir.
I would lastly say that if you want to avoid impacts, then you have to learn about earthquakes more. So misfortunes enter when window is left open to them. So learn more, avoid disasters. Thank you.
Thank you very much, sir. That's all for question answer session. Now I would request Major General N.K. Bindal, Executive Director of NIDM, for his concluding remarks. Over to you, sir.
Okay, so thank you, Anil Kater. It was a wonderful webinar in which the basic details of how earthquake is monitored and what are the difficulties and what are the tremendous number of challenges and what level of computation is required is really overwhelming. And but the confidence shown by the professors and the scientists in this gives us a lot of solace that we are on the right path, and maybe we will be setting examples in future for the world by forecasting earthquake to some extent, a lot of accuracy. And the steps being taken by National Center for Seismology are really commendable, for which I really thank Dr. B.K. Bansal for serving the country in such a noble way with his team. But I really thoroughly enjoyed this webinar, and I learned a lot, because so many things which we used to hear today was explained so vividly, each and every graph and every process, that I'm really thankful to the speakers, all speakers, for actually taking a class for us, I'll say, not a lecture. Yeah. But it was really good. I have no words to express my uh, appreciation. And participants also, they have asked a lot of questions, and very good questions at many places they have asked, which show their interest in the subject and their concern about the subject both. So I will again thank Professor Surya Prakash and Dr. Bansal and Dr. Suresh, Dr. Ravi Sinha, uh, and Dr. Harjeet, who was there, Anil Katet, everyone who was involved in this whole process for organizing this webinar. And maybe we can carry a few more webinars with the National Center for Seismology to make people aware about the challenges that are there when they talk about, because 99% of the population is not aware that earthquake cannot be predicted and why it cannot be predicted. So today's webinar was in one way trying to tell them what are the challenges involved, and I think this also needs to be expanded. The audience base needs to be expanded so that the message goes across that this is a very good area for research, and for research by various IITs and technical institutions, and like we have a and with collaboration, because the cost involved are so high, and the common resources are being shared, as we saw in the presentations, that it has to be a collaborative effort. It cannot be done by one institution on its own. So that collaboration is required, which can only be done at the National Center, for which National Center for Seismology has taken a lead, and I'm sure will take further lead in this and involve more and more stakeholders in coming up with a real-time monitoring system with real-time forecasting capability, rather than correlation in hindsight. These were the words used by Mr. Bansal in his opening address, which make a lot of meaning and which actually give out the present status of the earthquake forecasting and monitoring capability. So with this, I thank everyone. I thank all the participants, and my heartfelt thanks to all the speakers and Mr. Bansal for collaborating with the NIDM for this important webinar, and especially NIDM team led by Professor Surya Prakash for thinking of this topic and organizing it so wonderfully. Thank you so much. Thank you, Anil Katar.
Thank you very much, sir, for providing your concluding remarks. Disasters are a learning process. They provide us opportunity to examine what we have done so far, what mistakes we have made, and what improvement should we come to next. So we need to learn from each and every disaster to strengthen our strategies to combat the challenges of disaster in near future. Honorable Prime Minister also exhorted to ensure the opportunity to learn from a disaster is not wasted in his 10-point agenda for DRR. At the outset, I would like to thank our distinguished dignitaries of inaugural session, Major General Manoj Kumar Bindal, VSM Executive Director, NIDM, and Dr. B.K. Bansal, Director, National Center for Seismology, for gracing the webinar with their presence and providing valuable inputs in the webinar. I also take this opportunity to thank our distinguished speakers, Dr. G. Suresh, National Center for Seismology, Professor Ravi Sinha from IIT Bombay, and Professor Surya Prakash from NIDM for enlightening us with their respective expertise. I express a deep sense of gratitude to all our participants without whom this webinar wouldn't be possible. In the end, I will like to thank my colleague Dr. Harjeet Kaur and Sri Raju Thapa for their hard work and coordination in organizing this webinar. NIDM will be organizing a webinar on landslide risk reduction and resilience on next Tuesday, that is 18th August 2020. That is the date in 1998 when a massive landslide ripped away the entire village of Malpa in Pithoragarh district of Uttarakhand. Shortly, we will be opening the registration of the webinar. Interested participants can join us on that webinar. With these words, we move to the end of today's webinar. Thank you. Thank you all for joining us.